So guys, today we got a very interesting problem actually, and a new concept that I haven't talked about yet. So first I'll introduce the problem. So, prove that there is a number on the form 1, a bunch of ones, and then a bunch of zeros that is divisible by 2014. And we're gonna do this with the pigeonhole principle. So if you're not familiar with the pigeonhole principle, it is a really basic logical concept. It is the very basic logical concept that if you have more pigeons than you have pigeonholes, then either pigeons have to share pigeonholes or one pigeon goes without a pigeonhole. I don't know how pigeons do, but yeah, you get the point. If there are too many shapes for not enough boxes, for a lesser amount of boxes, then you have to put the shapes in the same boxes, or they don't fit. Yeah, you get the point. And this very simple concept actually deems very useful in sophisticated math problems. How do we do this? Okay, so firstly, we should note that a number on the form a bunch of ones and then a bunch of zeros can be written always as a bunch of ones, a number with only ones, minus a number with also only ones. So say that there are n ones and k zeros, then if we denote the number a, say I, as the number with I ones, say this is I ones here, then we know that this number here is equal to an minus ak. Right? Because we have a number with first we start out. Oh, sorry, the n shouldn't be over here. Sorry. Yeah, okay, I can do this. Sorry, n plus k. N plus k. So we start out with this whole number just filled with ones, and then we just subtract the k last ones with, well, yeah, ak. So that is n. I can do that. So you see n plus k. It says there, and there it's k. So now, okay, how do we use the pigeonhole principle for this? Well, if we start by denoting every number in this form, every number filled with only ones, as well, yeah, we already did, as ai. A with an index represents the number filled with ones, with I many ones. If we then consider this as a list and then create two new lists by putting up the modulus equation for 2014. So we know that any number can be written as, we call this then b index I times 2014 plus the remainder with index I. So here we have three sets. We have A, B, and R. So now it actually turns out that you can create infinite amounts of numbers on this form that are divisible by 2014, which kind of makes sense, because if you would find a solution, then you could just add a zero and it would still be divisible by 2014, right? But what we have to do here, okay, firstly we should note that, well, yeah, bi and ri are natural numbers, and that ri is greater than or equal to 0, greater than or equal to 0. Oh, sorry, we can actually disregard 0, because if it's 0, then it's already divisible. So it's greater than 0, and it's smaller than 2014, because then it would also be divisible. Meaning that there are 2013 r's, different values that any number in R can obtain. You could call this the range or whatever. So there are 2013 different R's here. And here is where the pigeonhole principle comes in. So then say that I generate more than 2013 AIs. I generate more than 2014 numbers which have 1 to 2014 ones in them. So I generate 1, 11, 101, all the way up to, well, the number with 2014 ones in a row. And that would then mean that every AI, every number with only ones in it, would then be associated to another number in the lists B and R, and that would mean that we have 2014 R's, but there can only be 2013 different R's. So therefore, two elements in R must be the same. Are you following along? Hope so, because I can't hear you. Anyway, so if I have I have generated 2014 elements in R, and since all the elements in R can only be of the numbers 1 up to 2013, therefore there has to be a duplicate. And if we say that we find these duplicates, and we call these indexes, what integers, what letters have I not used? I can use x and y. So if we find that rx is equal to ry, then what can we do then? If the numbers have the same residue, yeah, exactly. If they have the same remainder in modulus 2014, that would mean that the difference between them is divisible by 2014. And that is super quick and easy to prove. So then we just take ax or ay minus ax. And why is that divisible by 2014? Well, that is divisible by 2014 because that is equal to by minus bx, and multiplied by 2014, and then plus ry minus rx, and this thing here is equal to 0, right? That's what we stated before. So we only have this thing here, which is obviously, or which is always divisible by 2014, as long as these are not the same. And they will definitely not be the same, because if they were the same, then that would mean that they're in the same interval of multiples by 2014. And if the remainder is say this the same and the coefficient is the same, then they would just be the same number, which obviously cannot be, because every element in our set A is different, because we're adding a new one all the time. So yeah, therefore our proof is concluded. Hope you followed along, and yeah, that was basically everything for me. Thank you so much for watching, and make sure to like and subscribe. Have a good one. Bye bye.